Welcome back. The topic this week is there's a slight change, and what we are going to do, rather instead of jumping into the adiabatic hypothesis and link diagram theorem, we are going more to look at examples of diagrams and discussions of Pauli violating diagrams in terms of time-independent perturbation theory. Last week we prepared the ground for time-dependent perturbation theory, but I wanted to pick that topic up after we've done the discussions of diagrams, and there's something which is called the link diagram theorem, and we are going to link this with the exercises this week, exercise 1. So the first thing I want to do is actually to have a kind of summary of the diagram discussions, where we look at the diagrams in the particle Hall formalism and in the particle formalism. So when I say the particle formalism, that means that we set up the diagrams without a new vacuum state, but we just take the true vacuum state. And there are different ways of visualizing this, and sometimes it's easier to see some physical processes in a particle Hall formalisms, whereas other times it's easier to see things in a particle formalism. So in a way, I just wanted to bring up a kind of summary of diagram rules, and then we are going to dive into the exercise, this exercise 1, which is a nice illustration of perturbation theory, but also of some technicalities which deals with unlinked diagrams and also so-called Pauli violating diagrams. So in Rayleigh-Schrödinger perturbation theory, we produce something which is called unlinked diagrams. And these are unphysical diagrams because they will not depend on the number of particles. So they will have an unphysical dependence on the number of particles, and the energy is what normally we call an extensive property, which means that it scales as the number of particles times some constant. And these unlinked diagrams actually break that. This is a topic which is a little bit more subtle, and we will not have time to cover it properly. But if you're interested in that topic within many-body perturbation theory, we can discuss that. This is also important when we move on to copper cluster theory, because at the end, you're only looking at an expansion in terms of what we are going to call linked diagrams only. And I'm going to try to explain what this means, so that it doesn't come as a big surprise when you see this in the literature. Now, in the textbook of Shavit and Bartlett, in particular in this chapter 6, there is an attempt at the demonstration of the link diagram theorem with time-independent perturbation theory. Now, normally the way it's often proved is in terms of time-dependent perturbation theory, which allows for a slightly, you might suspect or doubt the wording easier way of proving it, but it's at least that's the way I normally prefer to show it. And if we get time, I will show the link diagram theorem. If not, I will just make a video where you can watch the video on the link diagram theorem. So in many of these type of many-body courses, people just state the link diagram theorem and say this is a theorem which applies to the system, and then we just use it. So the thing I wanted to do now is to switch back to the whiteboard and then have a discussion of this topic of unlinked diagrams, linked diagrams, and simply have a basic review of many-body perturbation theory and just look at what we have done. So this serves as a kind of summary, which we had here, the examples of diagrams and summary of perturbation theory. So let me switch back to the whiteboard. And when we've done with this kind of summary and discussion, we are going then to look at this exercise number 1 in the exercise set. So if we look at the many-body perturbation theory, what we have defined in many-body perturbation theory. And if we now look at diagrams of second order, what we did was to define this delta E of 1. This is the contribution to the correlation energy, which was then defined by a phi 0. And then we had this HI, which we normally put equal the interaction piece. This is the most standard approach in many-body perturbation theory. So V is equal to this interaction piece. And often in many-body perturbation theory, people start without a Hartree-Fock basis. If you have a Hartree-Fock basis, you have to be a little bit more careful in how you define this interaction part of the operator. And what we found then is that this can be rewritten, this delta E, when we calculated it in this basis, which we have defined as the new vacuum state or reference state. We found that this is equal to 1/2. And then we have the sum over ij, and then we have the sum over I, j, and v, and ij. And if we now don't want to use the anti-symmetrized matrix elements, this is given in terms of the direct term and the exchange term. Now, if you now look at this in what we call in the particle formalism, so and because the exercise asks you, exercise 1 this week, asks you to actually draw the diagrams in the particle formalism and with the new reference state. So in particle formalism, what this means is that you have the following set of states. So we would have an I1 here, and then we have an I2. So these are my attempts at writing the letter I. And then we have a given state here, ij. So now I should ii, and then I have a state ij. And these are my 2 whole states, or 2 states. This is in the particle formalism. And then this continues with all the other single particle states. So I would have an I of n minus 1, and this is the finally I of n. So this is the direct piece, and then we would write down the exchange piece, where we have similar terms, and I skipped the labels now, but then we have the exchange term. So this looks something like this. So this is in the what we normally call just the particle formalism, where we have the true vacuum state. And this is an II, and this is a state ij. So I keep this indexing I to indicate that these are states below the Fermi level. And then you have all the other remaining ones. So if we do things in the particle formalism, we have to keep track of all these particle states which are not contracted with interaction. Yeah.
Can I just?
Yeah, go ahead.
Is this the interaction?
Yeah.
Are you drawing the interaction or are you just drawing the states?
No, this is the interaction, right? So your Slater determinant, this phi 0, is actually given now by the product of all this I equal 1 up to n of ai dagger of 0. So what you're in principle, what you're doing now is that you're taking, when you look at this, you have a phi 0 here, and then you would just put all the lines here, which are now not contracted. And then you have your interaction piece, still not contracted. And then you have all these states, which are not contracted. And this is just your phi 0 here. So typically when you set up things in the particle formalism, you keep all the states which you have, and then you have just to set up all the possible contractions. So what you would have then, you would make a contraction with this one, you could make a contraction with that one, and then you could have a contraction here and here. And then you have all the other ones, the bystanding lines, which actually don't interact, but we're actually looking at the sum over all these possible contractions here. And if you look at the expression which we had, the expression, the sum, what we need to do then is actually to have a sum here over I and ij here. So we are then summing over all the possible contractions which can take place. And you see that when you run things in the particle formalism, things get a little bit unwieldy. If you have tons of single particle states, then you need to keep track of all of these. And that's why you typically switch to the particle Hall formalism, because then you're just looking at in the particle Hall formalism, then you simply sandwich or bring together the lines which are contracted. So when you do this in the particle Hall formalism, what you have then is that sum. So if you now look at this contraction phi of phi 0, this would then just be all the lines being contracted. So when I put arrows, that means that you have performed a contraction. When you don't see the arrow, that means we haven't done the contraction, as we defined early in the semester. So you would have I1 here, I2, etc., up to IN. So this is just a kind of a repeat of what we are doing. And what you typically would do that this should be in the particle Hall formalism. Actually, in particle Hall formalism. What we have then is that this contribution, if you now look at one of the specific ones, let's call this I1 and I2, or V of I1 and I2. And then we have minus, and then we have the exchange term of I2 of I1. What we do then is actually we rewrite this in terms of this closed loops. So this would be I1. And then we have a new closed loop, and this is I2. And then we have plus, and then we have the exchange term, which would typically be written like this. So we would have an I1 here, and then we have the exchange term, which is then an I2 here. Then, when you look at the contribution to the energy, what is common to do then is actually to, when you look at the doubles, the double sum which we have, so this is now given by a term which contains this term ij, and then I would have now you can write it like this. So this is I, this is j, and this is plus, and then I have this state I, this one. It doesn't matter which way you draw these arrows, like that. And it's common then to just write this out like this. So just put arrows on it, but you don't put the labels. So when you see a term like this is often in the literature something which indicates that you now are actually performing the summation. Now, when you need to calculate and set up the analytical expressions, that is when you have to use the diagram rules and write down all the indices for the states in and the states out. So it's pretty common just to rewrite it like this without the labels on it. So these are just definition, right?
Yeah. Without the factors as well.
Without the factors, because then you have to deduce the factors here. So like in this diagram here, you would have a pair of equivalent whole lines, which then begin at the same vertex and end at the same vertex. And that gives a factor of a half. And then you put the labels, ij, when you're summing up over the states here. So these are just in case when you're reading the literature, that you actually just need a kind of quick summary of what we have done when it comes to diagrammatic expressions. Because in the second midterm, we are going to look at a simplified model, the Perry model, which is actually in that paper I gave to Daniel and Håkon. And we are going to look at that from the point of view of many-body perturbation theory. And if we get time, we may sneak in copper cluster theory. But I guess time is a kind of luxury when we're getting close to the winter break. Okay, so let's now look at just repeat a little bit and look at the second order perturbation theory. And in Rayleigh-Schrödinger and in Briand-Wigner perturbation theory, the terms are almost the same. And one of the reasons why I bring this up now is that we are going to look at this in more detail in this exercise. So I just wanted to link the discussions here with the discussions of the exercise. And hopefully that is something which will aid you when you're going to look at the second midterm. Okay, so in this specific case, what we had is a summation over the intermediate states where m is different from 0. And in principle, that sum goes to infinity because we have an infinite amount of intermediate states. So this is a phi 0. And now I'm just putting in the interaction term. And then I had a phi of m. So these are Slater determinants of phi of m. And then I have v of phi 0. And this is divided with w0 minus wm here. And this operator q, just to quickly remind you, that is given by the sum over all these states different from 0 because we have only one state in this model space defined by the operator p. And these are idempotent operators, all of them. And this e, which we defined, is actually w0 minus h0. And then we had that h0 on a state phi of m, just to quickly remind you of this, is given by wm multiplied with phi of m. Now, when you then look at the diagrams you end up setting up when we perform the contractions, the way this is going to look like is as follows. So if we now take the state, which we have here, this specific state phi 0, we can now rewrite this in the following way. So let me just put it up in a more schematic way. So what we have, a schematic plot in the particle formalism. And then what we did was actually to move to the particle hole formalism. Schematic plot in particle formalism. So that means that we start with a true vacuum. So what we have then is a phi 0, which we represent by all these lines, and these are now uncontracted. Okay, so we have the n particles, and here we can actually have P1, P2, and up to P of n here. And then, so we haven't labeled yet the states, but these are actually the states which we call I1, I2, etc., because these are defined to be states below the Fermi level. Then what we have then is an interaction piece. So if you look at this one, so we have an interaction piece which comes here. And that means that we have an interaction here. And that brings in just a term which looks like this before we have done any contractions. And then we have the intermediate state. So we have a phi of m, or phi of m here. And this is given in terms of as the denominator as well. So what we would have now would be a new set of single particle states, which define now the intermediate states which we produce. And what we could do now is to mark one of these states as, or more of them, as states outside the Fermi level. So this is outside F. F is the Fermi level. So just keep in mind now that these states could be one particle, one hole, two particle, two hole, etc., types of excitations. And then we have a new term, V, which then gives us this term here. And then we have the final state, phi 0 here, which now has all the whole states, which we would typically label with an I1, I2, I3, I4, up to an IN here. And then we simply perform all the contractions. And if we look at this in the particle formalism, what we would get then would be something like this. So suppose now that we perform our contractions of one possible contribution, which we can get, is actually a contraction of this type, where we have a sum over A and B. So these are the states above the Fermi level. And then we have all the uncontracted guys. So this could be I1, this could be I2 here. And then this continues till a given state here, where we have an I, like this. And then we have an interaction piece. And then we have a state here, which is now a whole state, no, particle state, A and B. These are above the Fermi level. And then we get back to I of I. And then we get a new one. So now we have performed the contractions here. So this is an I of J. And then we have an I of J here. And this continues all the way up to the last one, which is now contracted with itself. So a typical contribution then, this order and perturbation theory, if we now are not looking at the exchange term, but we just look at the direct term here. So this would be a diagram. When we now look at it, since all the other ones just give Kronecker deltas. So every one of these, due to the contractions, is a Kronecker delta. So I have an I1 here, etc. So we normally skip them, right? There's no point in making a list of Kronecker deltas. So this means that what we would have then would be a diagram in the particle, the intermediate state which you see here, because now I'm not summing over the whole states. So mark here that there is no summation over I and J here. Okay. So I'm just looking at the summation over the particle states. And then I have to make these contractions with all possible states below the Fermi level. So this term here would now just be given by an I1, I, an IJ, and then I have V, and then I have AB of B, and then I have II and IJ here. And this is then divided when we take the denominators, epsilon I1, I plus epsilon IJ minus epsilon A minus epsilon B. So this is if we draw everything in the particle formalism. And then we know that we could draw this in the whole formalism, particle whole formalism. And in the particle whole formalism, what we would do then, when you look at these diagrams, is that we would take the term which you see here. So if we do that in the particle whole formalism, then we skip all the Kronecker deltas. And then we take the whole lines, the outgoing and incoming whole lines, and we will simply write this diagram, which you see now in the particle formalism here. This is now rewritten by bringing together these whole lines here and whole lines here, because these are the same states. So we would have a state A and a state B. And then we have an interaction vertex. And then we have the IJ and then the II here. So this is a diagram without the summations which we put up. Similarly, what we could have is the following diagram, another type of contribution which we could get. Is a contribution of the following type. So if we now look at this in the particle formalism, what we would have then would be something like this, I1, and then we have the contraction with I2 with itself. And then we get that term here, where we take the interaction piece, and then we have this I, we have an incoming IJ, no, II, and then we have the particle line A, and then we have an IJ, and then we have an IJ here. But then what we have is the same whole line which goes through here. So there's an I of I here. So that means that we have a whole line which comes in the same state, and this is not affected. And so this is just another possible contraction, because when you now look at the contractions you have here, the possible contractions you can make, there is nothing which hinders you in you having a one particle, one hole excitation. So that means that there will be only one particle state here, and all the other ones are whole states. So when we then perform the contractions, there can be a whole state which is contracted with a whole state in the interaction element. So keep in mind that this phi of m, that now contains a sum over many, many different types of Slater determinants. And since we have only a two-body interaction, since we are dealing with a term to second-order perturbation theory, we can at most produce two-particle, two-hole excitations, as we discussed. So this diagram here, when we now just complete it in the particle formalism, this translates in the particle hole formalism. Now I'm getting lazy, so I just use the shorthand PH for the particle hole formalism. So that diagram, if you now look at this whole state which we have, you take away all the single particle states which are contracted with themselves, because these are just Kronecker deltas. And then you have the interaction piece. And the way you would draw this one, since these are whole lines which enter and leave the diagram, you just simply rewrite them like this. So this would be an II here, and then I would have an II here. And then I have this contribution. So I have an IJ here, and then I have my particle state here. So what this means is that the whole line I, so this specific whole line here, what that is seeing now is a modification to its movement due to one particle, one hole excitation. So there's a one particle, one hole excitation here. So you can think, if you look at this intermediate state, is a one particle, one hole excitation. So one of the states below the Fermi level gets excited to a particle state. So that brings in a mixture in the ground state of a one particle, one hole state. And then it gets de-excited and goes back to the ground state again. So you have a bystanding fermion, which comes in and goes out. This fermion here, as you can see from this diagram, which sometimes it's easier to see the physical process when you look at it like this. So you have a whole line here, which now interacts with a one particle, one hole excitation. That's one way to read that diagram. So the particle here gets its motion adjusted by a one particle, one hole excitation. And then you would have similar contribution from, since you're making a sum now over all the possible contractions, you will have a sum over all these particle hole excitations. So a final term here, when you now look at this diagram, so the final contribution for this specific case, you would then have a sum over I, and then I'm just going to rewrite it in J and A, and you're going to have a diagram which is then written when you keep the sums, which is written like this, where you put the labels. So I'm just going to rewrite it instead of these subscripts. I'm just going to have a J and an A, and this is now normally written without any labels, and you will simply see it draw like this. Then when you want, so diagrams are one thing, but at the end, you have to compute something. And when you have to compute something, then you have actually to perform these summations. So that kind of contribution now, which represents a one particle, one hole excitation, is a contribution which now runs over two hole states and an intermediate particle states. So these are just examples of diagrams which you would put up in many-body perturbation theory, and this is to second order. Now, when you then, we can look at more contributions. Just some old notes which I want to wrap up again. So the if you look at, you can look at more contributions and more examples. So let's just bring in more examples. So the what we have is that we can have a diagram like this. So we have the, again, the I1, I2, etc. And then we can have a diagram which looks like this. So now I'm just writing this without the anti-symmetrized matrix elements. So let me just put it up here. So this is state AB, and then I would have something like this. So this is in the particle formalism. So this is an II, this is my IJ, and this is my II, and this is the IJ, and then I have the final one. And then what I'm going to do now is simply to rewrite this in the particle Hall formalism. So this becomes, without us looking at the explicit summations, this will now be given by a diagram which is going to look like this. So we have the particle state A to the right and to the left, and then we have the Hall states, and these are just two represented by crossing lines here. So I would have this one, and this will be my I of I, and this will be my I of J. So that's a way by which you would indicate an exchange diagram. Now, one of the things which we discussed last time is also the fact that when we look at these diagrams, it's normal to use the anti-symmetrized matrix elements. But then, when you want to calculate the diagram, it's common to open it up in one of these ways. And so you could open up a so-called Hugenholz diagram so that it becomes equal to the diagram which you see here now, the last one. But then when you're setting it up, you would then use anti-symmetrized matrix elements. So there are different ways of looking at it. You can treat explicitly the matrix elements as not anti-symmetrized, or you can include the anti-symmetrized matrices. So sometimes it can be a little bit confusing when you look into different textbooks about and try to decode what is what, as we discussed last time. But it's common to use so-called anti-symmetrized matrix elements, and that means that you just open up one of these diagrams like that, and they will, with anti-symmetrized matrix element, this is going to be topological equivalent with a diagram which looks like this. Sorry, this is a whole line. This is a particle line. And you would normally sandwich this one into a so-called Hugenholz diagram, which then looks like this. But when you want to calculate and set up the analytical expression for it, you would typically open it up. And which way you open it up, it should always give you the same contribution when you use anti-symmetrized matrix elements. And for this specific diagram, there are 4 specific ways you can open it up. Let's look at a further example here. It's always useful to look at examples. So let's take a new contribution. Now I'm getting a little bit lazy, so I'm just going to skip the intermediates, these labels on the single particle states, which get contracted with themselves. So this is a diagram where I now have a whole state, I. So it's the same type of diagram which we had before, but we are looking at the exchange term. And now this is in the particle formalism again. So I have a state A here, and then I have my whole state going out, I and IJ. And then we have the remaining bystanding single particles, or particles, which are where the single particle states are just contracted with each other. And this could now be written out in the following way, in the particle Hall formalism. It gets this more compact expression here. So we would have an IJ here, and then we have the interaction piece, and then we have the particle line going up. So this is A, and then we have a whole line I here, and then we have the I here. So that's a way by which you can actually rewrite that diagram there. So sometimes it's more handy to write a diagram in the particle formalism, and in other cases, it's perhaps more handy to write it in a particle Hall formalism. So sometimes it's a matter of taste. Which one is the most handy? The analytical expression should always be the same. And then you can go on with the third order. So if we want to exercise a little bit, we could now set up a third order diagram. So let's do that. So a third order contribution. This is just a possible one. And this is within the framework of Rayleigh-Schrödinger perturbation theory. So I'm just putting up an RS here. So if we look at that one, we could now have if we look at the sum over A, B, and C, so we could have a diagram which looks like this. So we have the whole states, I1, these are uncontracted, I2, and now we have a whole state here, which we call II. That. And we have a contraction here. And then I'm going to just draw possible contributions here. That. We have a whole state in. And then we have a particle state here. This will be A. This is B. And this is C. So I have my whole state here. I have my whole state here, I. And I have my ij here and my ij like this. And then I have a new whole state here, and then an ik, and then an ik here. And this goes to the final one, which is an I of n here. So that's a possible contraction I can get to third order in the Hamiltonian, in the interaction. And the thing you see now is that this looks like a free body interaction, because you actually have free particles which can interact due to the intermediate states. And if you look at the intermediate state which you have here, so this would actually be a two-particle one-hole excitation when you look at it like this. And this would also be a two-particle one-hole excitation. But this becomes actually an effective free body diagram. So when you go to third order interaction, you can actually produce this kind of effective free body diagrams. You can have them at second order as well. But if we now take this in the particle Hall formalism, this is a diagram which would look like, so we keep this summation over A, B, and C. We haven't done the summation over the whole states. But now what you would get would be a diagram. So this whole line, which you see here, that's something which can be brought into just one loop. So we would have the state I here. And now we have the intermediate state here. So we would now have a particle line which leaves here, a new particle line here. So this is B and A. And then we have an interaction term. So we have a particle line which goes this way. This is the particle line C. And then we have the whole line here, which is I of K. But then we have also the whole line, which you see here, this whole line here, which is our I of J here. So this is the way you could actually write this diagram. And it's often written in a more compact way when we now are summing over all whole states as well. So this would become a diagram which looks like this, when we now don't put labels on it, meaning that we are performing the summations here. So what we would have would be something which looks like this. Sorry, not that one. And then we just put arrows to indicate that we have whole lines and particle lines. So this will be a particle state, and this is a whole state. So this is also a contribution to the single particle energies. if you now think of this as a single particle state, which then sees a correction which comes due to a two-particle, two-hole excitations. So this is the way you would actually interpret that kind of diagram. Okay, so the next topic which we're going to look at is something which is a little bit more problematic. And these are so-called unlinked diagrams. Because when we go to third order in perturbation theory, we're actually going to produce unlinked diagrams. Unlinked diagrams plus Pauli violating diagrams. Now, if you look at all the examples we have seen now, these are examples of linked diagrams. And you can see that all the particle lines are linked through some kind of interaction. So that means that you cannot break it into pieces with one interaction times another interaction. So here, all the interactions are linked to either a particle line or a whole line. And that means that you cannot break it up in distinct pieces. So if you now go to many-body perturbation theory to third order, you can actually produce diagrams which look like this. So if you now go to third order in Rayleigh-Schrödinger perturbation theory in RS, then we could have contributions which look like this. So we could have a diagram where we have this term, and this is multiplied with a diagram of this type. This is in the particle formalism. So this would be a particle state. I'm just indicating this with an A and B, and the other ones are whole states. So this could be an I1, an I2, and then an I1, and an I2 here, and then I have an I3, and an I4, an I3, and an I4. So this is an example of a diagram which comes from the term which we had. So we had a phi 0 with V multiplied with phi 0. And this is multiplied with phi 0 with V and phi m times phi m. This is the intermediate states. V of phi 0. This is just one of the contributions. And then it has a denominator W0 minus Wm squared. So the energy is correct. Everything comes out with dimensionality energy. But in Rayleigh-Schrödinger perturbation theory, what we got to third order is a term which runs like this. So that can actually be generated by that term. But I could also generate this from the first term as well. So we have another term which looks like the following. So this is the term which comes with a minus sign. And then we have in Rayleigh-Schrödinger perturbation theory, let me just set it up to third order. This has a term which goes like, and now I'm writing it a little bit more compact way. It has V, and then we have multiply this with the operator Q, and then we have omega 0 minus H0, and then I have V, and then I have a new one, and then omega 0 minus H0 times V, and multiplied with phi 0. That's the first term. That can also produce, depending on how you make the contractions. Because remember now that you have, if you look back at the schematic figure we made, when I now go to third order, there will be an additional interaction, and there will be an additional term like this. And depending on which lines we contract with which, we can get a term like the one you see here, which is actually unlinked. So both of these terms can actually produce something which is unlinked. Now, the unlinked term, as I mentioned, have an unphysical particle dependence and actually just unwanted. So this term, so the third order term runs like this, and it has a minus, and then it has a term which goes like phi 0 or V of phi 0 multiplied with phi 0, and then I have V of Q of omega 0 minus H0, but this is now squared. and then I have multiplied with V of phi 0. So both of these terms can actually produce a term like that. But if you look at this one, you see that explicitly that you have this term, which becomes this term. And then you have this term here, which you can relate to this term. However, you would be able to construct such a diagram also from this term here. Now, there's something which we're going to discuss now in a kind of hand-waving way after the break. We're going to show that there's going to be a term like this from this term, which produces an unlinked diagram, but then gets cancelled by an unlinked diagram term here. And this leads to the discussions of something which are called poorly violating diagrams. There is an intermediate type of state which we are not going to produce, but we will discuss that after the break. So just to look at this diagram here, the way it would look like in the particle Hall formalism, in pH formalism, and then we take a small break. This diagram is going to look like this. Multiplied with a term like this, but it has an energy denominator, which is now squared compared to what we had previously. And now we're not putting labels on it. So these are all examples of diagrams which are so-called, this is not normally what we call an unlinked diagrams, because you see that we have actually two interaction pieces which do not couple together via particle or Hall lines. You could get another type of unlinked diagram to second order, but this is actually not going to appear. So there can be a second order diagram, which in the particle Hall formalism looks like this. But this does not appear, because if you take this in the particle formalism, it's going to look like something like this. But then we have an intermediate state here, where these are the same Hall states. And we have defined the intermediate states. So this is actually not allowed, this specific case, because this intermediate state here has to be defined by phi of m. And where phi of m is not included in the state phi 0. So when we are summing in many-body perturbation theory, we are summing over intermediate states which are not equal to those of the model space. So that means that this term here is a term which doesn't occur in many-body perturbation theory. But in principle, if you were to calculate it, it would give you a term like that, but it would have an energy denominator which would be 1 over 0. So this term is actually excluded by definition.
The single particle states could be in phi of m.
But now I'm going to put these as Hall states. So this would be an II, an IJ, and this is now an II and an IJ. So these are the same states.
Yeah.
But they could be different Hall states, but they are not allowed by definition due to the fact that we have defined intermediate states to exclude the model space states. So a contribution like this one doesn't appear in the formalism. I went a little bit over time here, but the reason why I wanted to bring up this is that, so what we're going to do now is to look at the examples of so-called unlinked diagrams. And what we brought up before the break was the expression for many-body perturbation theory in the Rayleigh-Schrödinger framework, where we now have the first term, which now produces both linked, but can also produce unlinked diagrams. And then we have the second term here. And what we're going to look at now is how we can actually get rid of these unlinked diagrams. and how they can be cancelled out. So if we now look at the, so I'm not going to give a formal proof of the link diagram theorem, but we're just going to look at examples and how diagrams can be cancelled. So let's look at a contribution to the first term. So let me quickly repeat the expressions we had. So we have the first term in third order perturbation theory, which runs like this. We just wrote it up before the break. And I'm just going to write in a more compact way this E, which is W0 minus H0. And then we have a V and a Q of E times V over phi 0. And this is minus, and there's phi 0. And then we have V and Q of E squared, V of phi 0. And this is multiplied with phi 0 of V of phi 0. And now I'm just setting the interaction term equal to the two-body interaction. So if you look at the first term, we could get a contribution which looks like this. And if we write this in the particle formalism, so we could now have a term like this. So we have whole states. So we could have an I1, an I2, an I3, no, I1, and an I2 here. And then we have a diagram here with an intermediate particle state. So this is an A and B. So you see now I'm having arrows because all contractions have been made. So this is an I3 and an I4. This is an I3 and an I4. So this gives rise to an unlinked diagram when we perform all the possible contractions. So even if the term looks like we're having an interaction with Q, a new interaction with Q, and a final interaction, it doesn't mean that it will produce only linked terms, which with linked, we mean that all interactions are connected to the other ones via a particle or a whole line. So this has an expression when we write it down. So if we put up the expression here, we would have an I1, and then I have an I2 here, an I3. I take the top interaction, an I4, and then I have a V, and I have an A and B, like this. And then I take the middle interaction, which is just an I1 with an I2, and then I have an I1 with an I2 here. And this is multiplied with an AB of V of an I3 and an I4. And this is divided by the denominator, which goes like I3 plus I4 minus, and then I have an epsilon A minus an epsilon B, and then I have an I3 plus an I4 minus an epsilon A minus an epsilon B. Now, if I then look at this one, this is going to have a term which comes from the second piece. So there will be, this will be cancelled. By, and if you now look at these contributions, so we have only 4 states below the Fermi level, right? So this is a 4-particle system. So there will be a term, if you now look at the second term here. So this will actually involve 4 particles, and this involves also 4 particles. And one of the terms is going to look like the following. So I'm going to have this one. So I have an I1, an I2, an I1, and an I2 here. And this contains now an interaction piece, which goes like this. And then I have the bystanding particle states. These are states below the Fermi level. So this would be the term which runs like phi 0 of V of phi 0. Yeah. And then it's going to have an additional term where I now have something like an I1 here, uncontracted with interaction, just with itself. And the same with I2 here. But then I have an interaction piece. So this is multiplied with. So I have a state A and a state B, and I have my I3, my I4, the I3 and the I4. And in here, I actually have the denominator squared, 1 over this E squared. And that denominator is the same as the previous one. So if you look at this term which you have here, so this specific term gives rise to the same denominator here. Now, in this particular case, what we have done is simply to write this explicitly in the particle formalism. And that means that we will have a diagram here, which when we now multiply everything, we have the same Kronecker deltas. And that means that we end up with a term which goes like this diagram, multiplied with that one. And that's the same as what we have here. So these two diagrams, one comes with a plus sign and the other one comes with a minus sign. So they cancel each other. So this is an example of a contraction which you will find in the first term, which cancels an unlinked diagram in the second term. So as I said, I'm showing this by examples without giving you the full proof. So the full proof is written in or given in time-independent formalism in Shavit and Bartlett's text in chapter 6. So this is a more kind of hand-waving way of showing that specific diagrams will cancel. Now, there's another interesting thing here, is that if we now look at another type of diagram, so let me just bring that up. There was another thing.
But just one quick question.
Yeah.
What is the physical interpretation of the diagrams not being?
So the physical, no, the unlinked diagrams don't have a physical interpretation because they give rise to unphysical dependencies of the number of particles. So in our case, when we do many-body perturbation theory, with the Rayleigh-Schrödinger perturbation theory, the reason why we get these unwanted terms is that we made an expansion in the propagator when we set up perturbation theory to different orders, where we expanded in the exact energy. The price we pay then is that at every order interaction, we have a term which goes like delta E, like in third order, there is a second order term multiplied with a first order term. So the price we paid, because we reorganized the Taylor expansion, is that we get an expansion in terms of the delta E. That means that we have terms where we actually produce diagrams which are not physical. And we can actually show, if you're interested, that these diagrams actually give rise to a non-physical dependence on the number of particles.
I guess my question was multiple. I meant like, what is the part of the physical reality that you're doing?
The part of the physical reality.
Yeah.
Yeah, okay. So there is something which now is interesting. If you look at the diagram which we also have here, this second diagram, if you take a closer look at it, this is a diagram which actually would break the Pauli principle. If you look at it, because you have I1 here and I2 here, and you have I1 and I2 there. So this is also an example of what's normally called a Pauli violating diagram.
Yeah, you have an interacting, you have interactions between I1 and I2 in one, and not interactions in the other. So
because then you have what you're looking at now. When you look at the state here, you're actually having a contribution which violates the Pauli principle. So this is an example of what's called a Pauli violating diagram as well. So these are non-physical contributions, but they ensure that you actually cancel unlinked diagrams in the different terms. So order by order perturbation theory, you can show that by summing freely over all intermediate states. So if you now sum freely, you will one break the Pauli principle, but by doing that, you also cancel terms which are unlinked. So that's the kind of benefit here. And you can show this order by order in many-body perturbation theory in a systematic way. The proof is a little bit convoluted, by the way. Yeah.
So in fourth order,
Yeah.
you would have minus a third term.
Yeah. Yeah.
Third order and,
Yeah.
and the minus the second order and
yeah.
Okay.
So what I thought of doing now is actually to bring up the exercise which we had this week, because that shows you how you can then cancel specific Pauli violating terms with unlinked terms. So that exercise contains, if you get the basic message in that exercise, you will see how you order by order will get something which contains only linked diagrams, which also don't violate the Pauli principle. But you have to sum freely in the basic expression, because that guarantees that you get rid of unwanted terms. Now, when you do Bruyère-Wigner perturbation theory, there is no problem with that, because you have a Taylor expansion where you expand in terms of the exact energy. So let's try to look at this in a more explicit way with a specific example. So the example we're going to look at now is this first exercise. So this is exercise 1, and that's the topic I wanted to bring up. And this is week 45. So in this specific case, we have a Hamiltonian. So we have defined it to be given by a one-body part. So we have a sum when we have only two single particle states. But so I equal 1 up to 2 here. There is an epsilon I. We have an AI dagger, AI. And then we have a term here where we now sum over I and J, but I is different from J, and it runs only from 1 to 2. And in this specific case, we have an AI and an AJ here. So this is going to be the interaction. And you could think of this as a single particle system. And we have two levels, epsilon 1 and epsilon 2. So when I write it like this, these are the energies of the two states. These are the exact energies with the interaction. And then we have also the unperturbed energies. So if we now look at the system here, and if we calculate the term in many-body perturbation theory, what we would have then for the ground state. So for the ground state, we would then have a delta E. So I'm going to write this as a delta E1. This contains now a phi 1. This is the computational basis. So I'm assuming now that I can rewrite this as an H0. And I can rewrite this as an interaction piece. And then I'm going to assume that I have a computational basis where phi 1 is an eigen state of H0. And this has an unperturbed energy, phi 1. And then I have an H0 acting on this phi 2. So that's my computational basis. Multiply with phi 2. And then if I use perturbation theory, then I should be able then to, if I stop at first order, so this is the first order for the ground state. So this should actually be given by this term here. Now, what you will see then, due to the definition of the operator, what we have then is an operator where I have I different from J, and it runs from 1 to 2. So what does that actually mean? For 0. So this is actually equal to 0. So that's, do you see that immediately without running any calculations? Because the operator now, the HI is pretty simple. So it's going to be lambda A1 dagger A2. So there is no possibility that they have an interacting term along the diagonals. This is also going to simplify the diagonalization, the exact diagonalization. So it means that if I look at my interaction piece, when I calculate these terms, phi1, h1, phi2, let me just set them up here. That's going to be equal to phi2, hi of phi1, and this is equal to lambda. And then what I have is that phi2 of hi of phi2 is equal to 0. So if I now go to many-body perturbation theory, and I am going to set up my terms here. So if I now look at delta E1 to second order, this is going to be equal to the following. So I will have since I only have now one intermediate state, which is phi2. So I'm going to define my model space. P is going to be given by phi1 of phi1, and Q is going to be simply phi2 of phi2 here. So that means that if I do second order perturbation theory, I'm going to have phi1, hi, phi2 here, and then I have my phi2, hi, and this is divided by now epsilon1 minus epsilon2. So now I'm thinking of the Rayleigh-Schrödinger perturbation theory, but if I do this in Bruyère-Wigner perturbation theory, so this is something which we would have to put a label RS, this is Rayleigh-Schrödinger. But then we have to be a little bit careful. If we look at Bruyère-Wigner, this is actually different. Then we would have a delta A12, which is now equal. And actually, let me also set up this term here is lambda squared of epsilon1 minus epsilon2. If I do Bruyère-Wigner perturbation theory, this is going to be given by E1, because then I have the exact energy. And then I have H0 as the intermediate state operator, and that gives me epsilon2 here. So there is a difference now between Rayleigh-Schrödinger perturbation theory and Bruyère-Wigner perturbation theory. Now let's take a look now at the third order. So we can now, if we take Bruyère-Wigner perturbation theory, the third order for this ground state, we are going to get terms which look like this, because now we have an intermediate state, and that means that we will get phi1 of hi, phi2, but then I have only one intermediate state of hi, this is phi2, multiplied with phi2, and hi with phi1, divided by, so this is Bruyère-Wigner, epsilon1 minus epsilon2, and then I have an epsilon1 minus an epsilon2 again. But there's something which you see here which is going to make life a little bit easier when you look at Bruyère-Wigner perturbation theory. So what strikes you as a kind of result here? What would the result actually be here?
It would be 0.
0, exactly. Because you will the only intermediate states you have are given by phi2. So that means that you will have intermediate states now which will have phi2 coupling to phi2.
But it's 0.
Because
it's a 2 in the middle.
Yeah.
Oh yeah, I thought it was the 1.
So the intermediate states will always look like that.
Yes.
So what you can see then by inspection then is that Bruyère-Wigner perturbation theory stops at second order. So for this simple example here, all the high order terms are equal to 0, because all the high order terms will have an intermediate states which connects with itself. And we have by definition said that the Hamiltonian is 0 for that specific case, for the interaction piece.
This is only for the single particle.
Yeah.
Because it's a single particle state.
No, but no, these are actually, you could think of these as many body states. You're not limited to think of this as a single particle state. It's just a two-level system. But here it's easier if you make the interpretations in terms of a single particle state. But it could just happen that your operator looks like this. And this acts on a many-body system. But your many-body states now, if we now just restrict ourselves to single particle system, in that specific case, which we are looking at now, then this term is exactly equal to 0. And all the other intermediate states will contain only phi2. Phi2 linking to phi2. So when I go to 4th order, I will get 0. 5th order, I will get 0. But Rayleigh-Schrödinger perturbation theory will not give 0. And then we have to be a little bit careful with what happens there. So if we look at Bruyère-Wigner perturbation theory, actually that terminates. So that means that in that specific case, the whole delta E 1, which is equal to E1 minus epsilon 1, that's the difference. This term here is simply equal. So we have a term to first order, which is just the lambda. Actually, the first order, we have 0, as we showed here. So that means that the energy here is actually given by lambda squared of E1 minus epsilon 2. So that means that the energy of the ground state in Bruyère-Wigner perturbation theory is given by epsilon 1 plus lambda squared of E1 minus epsilon 2. And what we're going to see now when we do, when we set up the matrix to diagonalize, that this is actually the exact result.
Do you, if the third order, the delta E3 was not 0,
yeah,
then you will get the term E to the third.
Oh yeah, yeah.
So in general, we always have to like solve a polynomial equation at the end.
Yeah, yeah, exactly, exactly. But then you would have to solve it iteratively for E1 by starting with a guess, because you would have E1 in the denominator. Actually, just to bring up that so you remember the expressions, let's now go back to our definitions of Bruyère-Wigner perturbation theory. So if we go back to what we did just some weeks ago, so we discussed many-body perturbation theory. So let's just bring that up. And in this specific case, when we look at the derivations here, what we ended up with when we do Bruyère-Wigner perturbation theory. So this is Rayleigh-Schrödinger perturbation theory, but in Bruyère-Wigner perturbation theory, what we had then, and I have to bring this up here, didn't I? Yeah, we just specified. So in Bruyère-Wigner perturbation theory, what you would get then would be terms like this, where we have the exact energy in the denominator. And since in our case, we have only one possible intermediate state, and since the interaction between the same state to the same state is equal to 0 by definition, the way we made the model, so we have no matrix elements along the diagonal, then all these high order terms disappear. And that simplifies the calculation within this model here.
But it doesn't have to converge the Bruyère-Wigner.
The Bruyère-Wigner doesn't, it may,
like
no,
yeah.
But you can actually rewrite this as a kind of matrix inversion problem. And because you can sum this up and get a closed form expression for it. And where you would have the exact energy minus H0 but minus Q times the interaction piece times. So you can actually rewrite this. If you sum up these terms here, you can actually rewrite that. And let me just put that up on the. So if you do Wigner perturbation theory, what you can show is that this delta E, 1 for the ground state, or B is given by phi 0. And then you would have a HI plus, and then you have Q, and then you have 1 divided by E1 minus H0 minus Q times HI, Q. So this also involves Q actually. So you could take away Q here. So you could actually, let me just take that one away. And this contains it has an element here, sorry. Times Q, oops. Q times H of I times, and this has an HI here multiplied with phi 0. So you can actually rewrite that summation in terms of this expression here. And this expression here, now since we actually have an interaction where you cannot connect the same states, then this actually terminates to second order. So you can write out this diagrammatically if we want to do that. In the particle formalism. And now we specify this to be a one-particle system, as we wrote in the exercise. So that means that you would have now a state 1 coming in, 1 here. And then you would have an interaction piece governed by this parameter lambda. And then you have the state 2. And then you have the lambda interaction piece, and you end up with the state 1 again. So in the particle Hall formalism, let me just write that one down here. If we do that, then we would now define the new ground state that will simply be given by an A2 dagger, A1, acting on the original vacuum state phi 0, where phi 0 is simply A1 dagger acting on the vacuum state here. So that means now that what we have, sorry, this will be the phi 2 state, sorry, phi 2. I actually was a little bit, this will be a phi 1 here, sorry. This is the way we define them. So in the particle Hall formalism, that state phi 2 is actually a particle excitation. Whereas what we have defined in the particle formalism, this is an A2 dagger acting on 0. So this is in the first, this is in the particle Hall formalism, and this will be in the particle formalism here. And if you want to draw the diagram, that means that this becomes equal to, so you have a particle state above the Fermi level, and then you have the whole state here. And this is a 1, and this is a 2. So these are the diagrams you would get in the particle Hall formalism. Now, the thing we're going to do now is to look at Rayleigh-Schrödinger perturbation theory. So let's take a look at that. Any questions? So let's do Rayleigh-Schrödinger perturbation theory to third order. And what we have then is that E1 is going to be replaced by epsilon 1 in the denominators. because now we are making a perturbation expansion or Taylor expansion in principle around epsilon 1 in the expansion. So delta E1 to third order in this specific case is going to look like as follows. So the expression will have a phi 1 of hi of phi 1, and we just saw that that is equal to 0 due to the way we have constructed interaction. And then we have a term which is going to be pretty similar to what we had in Rayleigh-Wigner perturbation theory, except that the denominator is different. So the whole thing with Rayleigh-Schrödinger perturbation theory is that we can calculate order by order all the terms because everything is known. So this would be given by epsilon 1 minus epsilon 2. But then we get the third order terms, and one of them is going to look like phi 1 of hi of phi 2. And then we get a phi 2 interacting with itself. And then I have a phi 2 of hi of phi 1. And this is divided by epsilon 1 minus epsilon 2 squared. But then I have this additional term where I now have a term which goes like phi 1 of hi of phi 1. So this is the unlinked diagram contribution which we get. Phi 1 of hi of phi 2. And this has a phi 2 hi of phi 1 divided by epsilon 1 minus epsilon 2 squared. And in this particular case, we can just read off the contribution immediately here. So to third order, there is no contribution here. So that means that to third order, we actually get something which is almost like Rayleigh-Wigner perturbation theory. We get epsilon 1 minus epsilon 2. And diagrammatically, in the particle formalism, this is going to look like this. So we have a state 2, we have a state 1 coming in, and we have a state 1 leaving. So the only difference now is that we have in Rayleigh-Schrödinger perturbation theory, we have a denominator which we can calculate.
In the second term, the first inner product, that's a 1 on the,
this one?
No, 2 lines down.
This one?
2 lines.
This one, yeah, that's a 1.
That's a 1.
That's a 1.
1. Yeah.
It's a 1, 1, yeah. Sorry. And this is 0, 0, and this one is 0. So that means that we're only left with the 1 term due to the simplicity of the Hamiltonian here. So what we could do now, we could actually try to set up the problem as an FCI problem. So if we now look at the matrix we have to FCI, so we would have a Hamiltonian matrix. And this Hamiltonian matrix is pretty easy to set up. So the matrix we get, H, is going to be equal to epsilon 1 on that diagonal. And then I have lambda, lambda, and epsilon 2. That's the matrix. So this is the same if we now think in terms of matrix elements. So this is phi 1, our computational basis with H, phi 1. The next one is phi 1 here. Let me just bring this up on the next line here, because then it's a little bit cleaner. So I would have phi 1 of H. This is the total Hamiltonian, phi 1. And since the interaction piece doesn't connect the same states, we get only a contribution from epsilon 1. And this is H, and then phi 2. And then I have the similar term here, over phi 2 over h, and then phi 1, and then phi 2 over h of phi 2. And that gives that simple matrix which we have here. And what we have then is that the eigenvalue problem, when we now diagonalize it, this should be pretty easy to do actually. We get the following energies. We have 1/2, and then we have a term epsilon 1 plus epsilon 2 here, and then it's plus minus, and then I have an epsilon 1 minus an epsilon 2 squared plus 4 times lambda squared. So this is the eigenvalue equation here. And if we now expand this, we can perform a Taylor expansion of this equation here. Actually, these eigenvalues, you will see immediately that these eigenvalues, if you look at the lowest one, the lowest eigenvalue is going to be exactly the same as the one which we found in Braying-Wigner perturbation theory. So in Braying-Wigner perturbation theory, if you now simply multiply with E1 minus epsilon 2 here on both sides, then you can rewrite that one, because this would be, if you look at this one, if you multiply out, you would have E1 minus epsilon 1 multiplied with E minus epsilon 2. And then this is given by, if I now bring lambda over to the other side, I would then have a minus lambda squared. And this is the equation we want to solve, right? And this is the same if I now take my matrix equation, which I have here. If I now take the eigenvalue, solve the eigenvalue problem by setting up the determinant and find the characteristic polynomial, I get exactly the same expression which you see here, this one. So the only thing is that here I have E1 when I look at that specific eigenvalue. That sound okay? So we get this two eigenvalue problem, and the thing we are going to do now is to make a Taylor expansion, and we can now rewrite this equation here in terms of 1/2. And I have an epsilon 1 plus an epsilon 2 minus, and then I take an epsilon 2 minus an epsilon 1 here, and then I have the square root of 1 plus 4 times lambda squared divided by epsilon 2 minus epsilon 1 squared. And then I Taylor expand with lambda divided by epsilon 2 minus epsilon 1. So that means that what I get then is something which runs like epsilon 1 when I Taylor expand it now. So I'm going to rewrite that one. So I have factor over 1/2 epsilon 1 plus epsilon 2 minus epsilon 2 minus epsilon 1. And this is multiplied with 1 plus 4 times lambda squared of 2 divided by epsilon 2 minus epsilon 1 squared. And then I have minus 2 times lambda to the power of 4 divided by epsilon 2 minus epsilon 1 to the power of 4, and then higher order terms here, like that, and end of parenthesis. And when I recombine it, what you will see then is that I get epsilon 1, because I have now in the first term here, when I multiply it with 1, this term, you see now that the epsilon 2 cancels with that one. But then I have epsilon 1 plus epsilon 1, but I have a factor of 1/2 here, so that gives me 1. So that means that the term multiplied with 1 there gives me just epsilon 1. And then I have minus lambda squared. And then I have epsilon 2 minus epsilon 1. And if you look back at Rayleigh-Schrödinger perturbation theory, what I had is epsilon 1 minus epsilon 2. And if I just interchange them, I have minus in front of the term there, right? And then I get my next term, which goes like lambda to the power of 4 divided by epsilon 2 minus epsilon 1 to the power of 3. And this goes on with higher and higher order terms. So what we are going to analyze after the break is actually this fourth order term, because now we have something which is fourth order interaction. So when we look at the Taylor expansion here, if you take a closer look at the Taylor expansion of the exact result, what we have then is something which to second order here in the Taylor expansion is the same as we get with Rayleigh-Schrödinger perturbation theory. So we started with the exact answer here, and then we simply reshuffle things in terms of the interaction divided by the energy denominator. Now, one thing which is also neat to see from this case is that you see that this expansion will only converge if lambda divided by epsilon 2 minus epsilon 1 is smaller than 1, the absolute value. So that tells you a lot about how perturbation theory will converge or not converge depending on the ratio between the interaction and the single particle spacing. So like in atomic physics, we often have a big gap between the whole states and the particle states, and the interaction is weak. Perturbation theory works very well. If you have a very small gap around the Fermi level, then perturbation theory may break down, even if the interaction is weak. So it's actually the ratio here which matters. So if you look at a system like quantum dots, this has a counterintuitive result because quantum dots are electrons in a harmonic oscillator well. So if you make the well very, very wide, that means that your harmonic oscillator energies become denser and denser, the spacing. But the particles on average, they are far apart from each other. The interaction matrix elements are also weak, but they are not weak enough because if you think of the Coulomb interaction, it has an infinite range. So there's a delicate balance between the strength of the interaction in that case and the spacing around the Fermi level, which makes perturbation theory for such a system, which is weakly interacting, to break down, simply because the spacing changes. But just to remind you of that, if you think of a harmonic oscillator well, so let me just show that here. Then you have a set of single particle energies, and you would define a Fermi level here. So if this spacing becomes denser and denser, so the harmonic oscillator energies are given by in 2 dimensions of 2n plus L plus 3/2. So if this frequency becomes smaller and smaller because the well becomes wider and wider, then the particles on average are far apart from each other. So you would expect them to interact less, which they do. However, if you think of perturbation theory, perturbation theory breaks down even if the system is weakly interacting, because the spacing between the single particle energies is getting smaller and smaller and smaller. And that means that the term you see here becomes more and more important, even if lambda is weak. So it's always the ratio which matters. So there are some counterintuitive cases because you would expect that since the particles are getting more and more apart from each other on average, because then you would have, if 2 electrons move here, you could have 1 here and 1 here, and they would be interacting weakly. But the Coulomb interaction, which is the interaction in that case, has an infinite range. So it's not given which kind of ratio you may get. So you have actually to study it from case to case. And this simple problem, which we are looking at now, contains a lot of the kind of basic problems which you will encounter in many-body perturbation theory.
You can do this in the degenerate case?
Yeah.
But if the single particle and are equal, you get to something like d2 minus or...
So this is for the non-degenerate ground state.
Yes.
If you have a degenerate ground state, you have to be careful, because then you have, if you have a degenerate ground state, it means that your ground state would be a linear combination of slave electrons.
And of the single particle energies are degenerate.
Yeah, then you could not do this.
Yes.
So then you would have to use what's called degenerate perturbation theory. So this assumes that the ground state, there's a unique ground state.
Because in E2 or epsilon 2 here is always above the firm level.
It's always assumed to be. Yeah.
So if you have states above the firm level that has the same energy,
then you run into and this is this harmonic oscillator case where the spacing becomes smaller and smaller and smaller, and at a certain point you reach close to degeneracy. Then your admixture of one particle, one Hall states is going to be huge. So you will get all kinds of excitations. Even if the interaction is weak, you will get strong correlations.
The perturbation is too big.
Yeah, the perturbation is simply too big, actually. So perturbation theory is nice, it's easy to use, but it may not converge. But it gives you what if you do second order, which many people, like in atomic physics and quantum chemistry, typically do, you can do something which is called Möller-Plesset perturbation theory, which is essentially many-body perturbation theory to second order. And from a computational point of view, it's quick. And it serves as a first estimate. Actually, in the midterm, you're going to calculate perturbation theory to second order and compare that with an exact diagonalization case, because you're going to get a 6x6 matrix. So you will have the exact answers, and you can compare that with the many-body perturbation theory as a function of the strength of the interaction. But this simple example here, the reason why I wanted to emphasize is that this simple example conveys much of the basic essential features of perturbation theory. We simplified it by not having diagonal matrix elements, but in general, I mean, you can add a complexity here by having diagonal matrix elements as well. But then you would get more complicated contributions to second order, third order, and fourth order, and so on.
This fourth order lambda.
Yeah.
Does come from the fourth order term. And it's minus.
Yeah. We will see that after the break here. So how that comes through. And that brings back unlinked diagrams and polyviolating diagrams as well. So we're going to use that as an example to illustrate these concepts. I'm going to put on the recording. Now, I will pause. So when we make the Taylor expansion of the exact solution, we can then see that there are terms which are going to correspond to different orders in perturbation theory. And if we connect with the Bruyère-Wigner result, if we write that one out, so if we take Bruyère-Wigner perturbation theory for this ground state, and I'm going to put a BW here to indicate that this is Bruyère-Wigner. This was given by lambda squared of E1 minus epsilon 2 here. And that's something which we can rewrite as lambda squared of epsilon 1 minus epsilon 2 plus this delta E1. And you see now where the delta E1 comes in when you do many-body perturbation theory with Rayleigh-Schrödinger perturbation theory. Because we can now expand around this delta E1. So that means that when you go to different orders in the Taylor expansion, you will get the terms multiplied with delta E1. And then when you go to fourth order, if we now write down many-body perturbation theory to fourth order, or if we just look at this expansion here, if we take a closer look at this one, this is something which we can rewrite as a lambda squared of epsilon 1 minus epsilon 2. And this is essentially the way we derived Rayleigh-Schrödinger perturbation theory. We can rewrite this one like this. And then when we expand it, this gives us simply lambda squared of epsilon 1 minus epsilon 2 here. And then we have a 1 minus delta E1 divided by epsilon 1 minus epsilon 2. And then we get plus delta E1 squared. And then we have epsilon 1 minus epsilon 2 squared. And this continues like that. So when we did many-body perturbation theory and the Rayleigh-Schrödinger approach, where we replaced the exact energy with the unperturbed energy, so that we have terms we can evaluate at every order, because we know every single term. Epsilon 1 is defined, epsilon 2 is defined, lambda is defined. Lambda would just be the interaction matrix elements. So that means that the benefit of Rayleigh-Schrödinger perturbation theory is that every order, we actually do have a recipe for calculating every single ingredient in that given order perturbation theory. Now, when we now look at what we had, this becomes equal to lambda squared of epsilon 1 minus epsilon 2 here. And then we had 1 minus. And now we have to remember now that with delta E1 squared here is something which would then become lambda squared divided by epsilon 1 minus epsilon 2. This is squared, etc., etc. Now, the thing we have to see now is that in Breuer-Wigner perturbation theory, it gives only terms of second order, since all the high order terms are equal to 0. And you will see that also if you take a fourth order term, you will see that everything is just 0. So Breuer-Wigner gives also the same result as the exact diagonalization. If we now expand this Breuer-Wigner perturbation theory, we actually get the same results as we have with Rayleigh-Schrödinger perturbation theory. And the fourth order correction to Rayleigh-Schrödinger perturbation theory is now going to be given by this term here, and obviously multiplied with that one. So we need to see how this comes through. But let's now look at the terms we would get in fourth order perturbation theory with Rayleigh-Schrödinger theory. So let's take a closer look at delta E for the ground state to fourth order with Rayleigh-Schrödinger perturbation theory. So what we would get then, when we look at the explicit fourth order contribution, and we perform this Taylor expansion we discussed some weeks ago, this runs like Q divided by E, and this E is epsilon 1 minus epsilon 2 in our case, or actually this E is epsilon 1 formally minus H0. So these are all operators. And what I have then formally is H1, and then I have a Q of E, H1, Q divided by E of H1. And what I'm doing now, I'm skipping here the phi 0 or the phi 1 term. So I'm just writing this in a more compact way, just to save notation here. So H1, and this goes like Q of E, and then I have the expectation value of H1, and then I have Q divided by E, and then H1, Q divided by E of H1. That's the next term. We actually do get 5 terms. So minus, and then I have an H1 of Q divided by E, an H1 of Q divided by E, and now I would have the interaction piece here, the unlinked, the one which gives rise to an unlinked diagram in there, times H1. And this just never stops, eh? Okay, so I get H1 of Q of E of H1 Q of E, and then I have an H1 again, and then I have a Q divided by E, and then I have an H1. And finally, I have a term which goes like minus H1 Q divided by E, and then I have a second order term here. So when I do the Taylor expansion in terms of this delta E term and got Rayleigh-Schrödinger perturbation theory, these are the terms which I would get to a fourth order perturbation theory. So what we have to keep in mind now is that all the terms which involve phi 1 H1 and phi1 are equal to phi2. With this specific model, we are actually getting rid of all the diagonal terms. So these are actually exactly equal to 0. So what happens now is the following. If you look at the different contributions we have, it means that we would have this term here, that would pop up here. It pops up here, here, here. In addition, we would have a term here where we now have phi2 connecting with phi2 in here, which is also 0. So it means that the only term which survives here is actually the term which you see down here, because this one, it contains now many-body perturbation theory to second order in here. So that's a distinct term. And then it has a new term with second order to many-body perturbation theory. So if we look at that specific term, the last term here, if we dissect that one, so let's take a closer look at this term because that's the only non-zero one. So this becomes 0, this is 0, this is 0, and the same with this term here, due to the Hamiltonian which we have constructed. So the only term which survives then is this delta E4, correction to the ground state, which is equal to minus H1 of Q divided by E. And here we have many-body perturbation theory to second order, E of H1. And this is multiplied with Q of E, and this has an H1 here. So if we open it up now, this is going to contain, if you look at this specific term, this is nothing but phi1 of HI with phi2, and then we have phi2. So this is just a constant, a scalar. And this contains epsilon 1 minus epsilon 2 here. And in our case, this is the same as lambda squared divided by epsilon 1 minus epsilon 2. If we then look at the next term, so what we are going to have then, so we have this lambda squared of epsilon 1 minus epsilon 2, and this is multiplied with phi 1, and then I have my Q over E, HI, and then I have a new Q over E of HI of phi 1, and this is nothing but lambda squared of epsilon 1 minus epsilon 2 here, and then I have my phi 1. So Q squared is equal to Q. So I get a phi 1, and I have an H1 here of phi 2 of H1 of phi 1. And this is divided by epsilon 1 minus epsilon 2 squared. And with that, what we end up with is a term which goes like lambda to the power of 4 of epsilon 1 minus epsilon 2 cubed, which we again can rewrite as minus lambda to the power of 4 divided by epsilon 2 minus epsilon 1 cubed. And this is a term which we got in previously when we did the Taylor expansion. If we now go back here, we see that when we made a Taylor expansion here, we got a term which had a sign of epsilon plus this lambda 4 of epsilon 2 minus epsilon 1, which means that if we reorder things in terms of the correlation energy, we see now that we actually, if we add the second order term, what we are going to get then is that Rayleigh-Schrödinger perturbation theory gives a contribution to the ground state. If we are now include second order plus fourth order, so to third order we had just 0. So this is the same as lambda squared divided by epsilon 1 minus epsilon 2 squared minus lambda to the power of 4 of epsilon 2 minus epsilon 1, which again is just lambda squared. And I can rewrite this as epsilon 2 minus epsilon 1 squared minus lambda to the power of 4, epsilon 2 minus epsilon 1 to the power of 4. So if we now want to look at diagrams, the diagrams which contribute now, if we look a little bit closer at the expression here, we're actually going to get two diagrams. So if you now look carefully here, what we would have is an interaction vertex where we have a, so let's just look at the diagrammatic terms which we have. So we would have a term which looks like this in the particle formalism. So we have diagram 1 here, 1. And then we have the intermediate state 2 here. So this is state 1. And then we have another diagram which looks like this. And then we have a 1 here, we have a 2 here, and we have a 1 here. So this would be the terms if we now just write back what we have. So we have a term which runs like minus. We have an H, let me just write it out here. And then we have an HI. And then this is multiplied with a Q divided by E. And then we have an intermediate second order contribution, which is the one which we have to the right here. So let me just bring that one. Let's write out everything in detail. One, and then I have an HI of Q divided by E, and then I have an HI of phi 1, and this is then multiplied with Q divided by E, HI with phi 1 here. So this becomes equal when we write everything out in terms of these two states. I have I, and then I have a phi 2. This contains a denominator, but now I'm going to write this out. So we have a phi 1 of H1, phi 2, phi 2 of H1 of phi 1. And this is divided by epsilon 1 minus epsilon 2, and this is multiplied again with phi 2, sorry. So this contains that one. And this would now be multiplied with phi 2 of HI of phi 1 divided by epsilon 1 minus epsilon 2 squared. So you could now think of you having an interaction here, which could now be this one. So that brings it into state 2. And at the same time, there is a new contribution which comes in here to second order. And then you have finally this contribution here. Now, this is an unlinked diagram, but it's also a Pauli violating diagram, because you see that you have the intermediate states here with 2 and 2. So if these are fermions, you should not be able to have an intermediate state here where you end up with the same contributions. And at the same time, you also have a Pauli violating term here. And it's an unlinked diagram. Now, when we now look at the contributions you have, in order to understand this specific term, what you could do now is actually to, if we now go to the perturbation, to the particle Hall formalism, we can, or let's just stay with this one. So what we can see now, when we look at the contributions here, there will be a corresponding one, which is going to cancel that term. But let me just write this out here. So we can write this out in a slightly different way. So we have 2, 1, 1, and then I have a 1. If I now just add 0 here in terms of a new diagram, so I'm going to write this one as a diagram like this. And then I'm going to take this as an exchange diagram. So this is a 2, it's a 1, it's a 2, and then I'll write it like this, 1, 1. And now I'm just adding 0 here. So that means that I have this diagram minus this one. And then I have this term here. Let's put arrows on it. 1, 2, 1. And then I have this diagram here. One, 2, like this. So simply adding and subtracting a contribution here. If I now look at the second diagram, this is actually an example of what is a link diagram, the last one. And if you now look at the different terms, let's call this 1 and 2 here, and 3. If we look at that one in the particle whole representation, if we take 1 plus 2 here, that's going to look like this. So we have a closed loop here, and we have this term. This is a particle state, and then we would have a new closed loop like this. And then we have plus a diagram which looks like this. So let me try to draw it correctly. So it has a particle line here. This is a state 2. So 2, 1, and this is 2 and 1. And now I have this term here. So I have 1 here, 1 and 2 here, and I have a 2 here. So if I look at these diagrams here, you will see now that this one has, these give actually rise to the same contributions. So this has 2 holes and 2 loops. It gives rise to a plus sign. This diagram here has 2 hole states and 1 loop. So that gives rise to a minus sign. So these 2 diagrams, when we set up the expression, they're actually going to cancel each other. But then I have an additional contribution, which comes with the similar contribution like this one, which was the one which we added and subtracted here. So there's going to be a contribution like that. So when I'm setting up the different contractions, there will be diagrams which will cancel each other. And the last term, which we have in this term here, is actually a term which doesn't break the Pauli principle. And you can see that when you write it down in the particle whole formalism. So that means that you're just left with final contribution. So we are left with term which runs like this, which we added and subtracted this term. So 2, and then we have a state like this. 1, 1, and then we have a state 2 here. And this is a term when we write it out, which gives rise to this minus lambda squared of epsilon 2 minus epsilon 1 cubed. when we set in the energy denominators as well. So that explains the term which we get when we now cancel these diagrams which are unlinked with a diagram which is linked. So actually, this diagram which you see here is actually a linked diagram. And this is a diagram which comes from one of these contributions. So we didn't set up all the contributions, but these two terms here, one of them cancels this diagram and the other one actually leaves us with a contribution which is non-zero. And that brings us back to the final expression which we got when we run through the analytical derivations. So at every order in perturbation theory, there will be unlinked diagrams, but they will be cancelled by other diagrams, which can be Pauli violating or non-Pauli violating diagrams. So order by order, if we now sum freely over all the intermediate states, we will ensure that we will be able to cancel so-called unlinked diagrams. And we haven't showed the linked diagram theorem, but it means that if we, I mean, these were just demonstrations which I wanted to, in a way, to argue for what is going to take place order by order. The price we pay when we do many-body perturbation theory is that we have an expression which will depend on the correlation energy. In principle, you produce unlinked diagrams, but these are cancelled exactly by other diagrams, which can be either Pauli violating ones or non-Pauli violating ones. And so you can show order by order that what you're left with is only linked diagrams. But then the assumption is that you have actually to sum freely over all the intermediate states. However, the diagrams which you're left with do not break the Pauli principle, and they are all linked. So the next topic which we are going to deal with, and I think it's a good point to stop here, is the derivation of time-dependent perturbation theory. And this is something which I'm going to put up as a recording, which you can then look at. And then next week, we will dive into copper cluster theory, which will be our last topic. So the time-dependent perturbation theory stuff is something which we are not going to use, but I'm going to put it in as an additional item, which hopefully gives you a kind of nice link with the time-dependent formulations, which is also very useful to have seen. So in most textbooks, they cover many-body perturbation theory in terms of time-independent many-body perturbation theory. The time-dependent ones gives often a more kind of physical, intuitive way of approaching the diagrammatic expressions and also the different terms in many-body perturbation theory. But there I'm just going to make a video. We will not, as I said, next week we are going to have the quantum computing school. So that means that we won't have a regular lecture. But we're going also to present the midterm by next week. So, and we are going to have a exercise session where we can start looking at the midterm from 8 to 10 next Friday.